Dear viewers, welcome to the final presentation of my graduation thesis on the topic Improving the Use of Surgical Suction Pumps in Sierra Leone. In low to middle income countries, more than 95% of the medical equipment are devices donated by NGOs. Whether new or refurbished second-hand devices, around 70% of them end up working improperly or not working at all within just a few years. The most prominent reasons for that are the lack of consumables, spare parts, skilled maintenance staff, and the infrastructural limitations of the context.
The suction is not working.
This video shows a common situation during the use of the surgical suction pump at Masanga Hospital in Sierra Leone. Like with most donated medical devices, the lack of compatible consumables and the hospital's frequent power cuts hinder the use of the device very frequently. A suction pump is a surgical device used for removal of biological fluids and gases from the operating field by applying negative pressure. The suction pump is used together with collection pods, where the suction media is collected, and medical tubes and catheters that transport the suction media from the patient to the collection pod. The general lack of consumables at the hospital led to a dimensional mismatch between the suction pump's consumables, a problem that they are currently solving by taping the consumables together with glue tape. Although functional, for short-term use, this solution results in lowered suction pressure and the risk of disconnection of the components and leaking of biological fluids, which could result harm the patient, the staff, and the device itself. The second challenge in the use of the pump are the frequent power cuts in Masanga, during which the suction pump stops working, sometimes even in the middle of a surgical procedure, risking the success of the procedure. Given these challenges, a decision was made with the client to focus the project on solving the dimensional mismatch between the medical consumables used with the pump and powering the device independently from the hospital's solar grid. Because of their different nature, the two challenges were converted into two sub-projects, or the two subsystems of this project: System Connect and System Power. Before continuing further, a quick introduction of the client. Masanga Hospital is a rural hospital located in the heart of Sierra Leone. The hospital was reopened in 2006 after being destroyed by Sierra Leone's civil war. From the reopening to this day, the recovery of the hospital relies on three pillars: healthcare, education, and entrepreneurship. About 10,000 patients are treated and 500 babies are delivered annually. 10 to 20 surgical procedures are performed weekly, from obstetric procedures to hernias, skin grafts, and amputations. Masanga is the primary healthcare center for the surgical training program in Sierra Leone. Their 3D printing lab, developed together with Radboud Medical Center from the Netherlands, is engaged in 3D printing prostheses for amputees. Their future goal is to engage in 3D printing of spare parts for their medical devices. This project aims to deliver a frugal design innovation to solve the introduced challenges. Some of the most important factors of frugal innovation in healthcare include testing and validation of the design solution, engagement of the local staff in the design process, mapping availability of clean water and power, keeping in mind storage conditions in the context, the availability of maintenance staff, knowing the supply chain limitations, mining the environment, and mapping of local available resources. Balancing these factors is essential in order to have a design solution that will benefit healthcare in the chosen context, by making sure that the solution actually fits the context of use and the end user. An in-depth contextual analysis was performed on Sierra Leone as the context country, Masanga Hospital as the operational environment of the device, and the operation room as the device's immediate environment. The contextual analysis helped to map the contextual limitations and opportunities and all the defining factors that could influence the final design solutions for the challenges. These factors served as guidance during the design process. Now let's get back to the project. In high-income country hospitals, suction consumables are connected using medical tubing connectors that fit different sizes of tubes. They usually come built into the tubing and are most often specific for every manufacturer. Contextual research show that due to supply chain limitations, the lack of medical device industries, and infrastructural challenges, procurement of the off-the-shelf medical connectors is not possible for Masanga Hospital. The unpredictable availability and dimensions of the consumables and the outdated equipment in Masanga require a customizable design for the connectors, and a manufacturing or procurement process that is independent from Masanga's supply chain. After multiple prototyping events and analysis of possible manufacturing scenarios for Masanga, local 3D printing of the connectors at the hospital's 3D printing lab was chosen as the best manufacturing scenario for the connectors, as it allows for a customizable, easily reproducible design that does not depend on Masanga's supply chain. Unlike in developed hospital, consumables in Masanga are not disposed of, but washed and reused after every surgery. In order to fit the organizational behavior of the hospital and the safety requirements for the connectors, the final decision was to develop 3D printed, reusable, watertight tubing connectors that would improve the use of the suction pump. The development of the connectors was tackled in 3 phases. Phase number 1, embodiment design, where the performance goals of the connectors will be achieved while preparing for manufacturing. Phase 2, design for manufacturing, focused on achieving set goals and their specific requirements while preparing for material choice. And Phase 3, material choice, where the final testing of the chosen materials is done. The connectors were developed to be stiff, with a barbed side that would fit multiple tube diameters, and a cylindrical side to connect to the collection pot. The embodiment would result with safer connection points between the components, improved suction flow, and faster preparation of the suction. Through multiple ideations, the internal and external geometries of the connectors were improved for better gripping of the suction tubes and uninterrupted flow of the suction media. 70 prototypes and endless failures later, the 3D printing slicer settings were finally adjusted to achieve proper layer adhesion to prevent formation of holes or cracks, good overhang settings for optimal bar bed sharpness, and suitable printing speed and cooling speed adapted for printing of small perimeters. A low layer height, combined with lower printing speed and lowered fan speed, result in watertight connectors with sharp barb edges and smooth inner and outer surfaces. With a well-calibrated printer for guaranteed quality and layer adhesion. The final achievement was printing a sequence of 5 watertight tubing connectors that satisfy the goals set in the embodiment phase. The last and final quest to conquer was picking a material that would allow for reuse of the connectors. PETG and ABS as material options were tested against environmental effects during storage and change of mechanical properties due to chemical treatment. Both materials performed well, but PETG was chosen as the suitable material for the production of the reusable 3D printed connectors due to its impeccable water tightness properties. Although I was not able to visit the context, the connectors were. The nursing staff at Masanga helped and performed a usability and performance test with the connectors.
I'm Aliu, ACC, a state registered nurse and also a nurse anesthetist in Masanga Hospital. I use this suction machine normally for patients to suck out blood during surgery, during laparotomy surgeries, for the surgeon to use them to collect fluid from the abdomen. I also use this suction to suck out mucus from my patient's mouth to prevent them from aspiration. So this suction, it fits to the port here with these connectors.
I'll just show this bit quickly. So
with this connector.
Okay, we're attaching.
With this connector fits well in the port, but normally it's supposed to be flexible enough to fit well, or else it breaks. And I connect the tube from the suction machine. I had another tube that I will connect. I connect to this port. The other connector that we got from the project here, it works well, and you can also fix it from the tube from the port. Now I connected a catheter tube. This tube used to go to the patient to suck out all secretions, all gastric contents, or all, because there is high pressure and there is more fluid sucking out. And when the pressure is low, there is tendency that the suction is low also.
So there's a litre in here,
Yeah, it's a liter.
and we are on the maximum pressure,
Yeah, we are on the maximum pressure, that is a liter.
and we'll wait until it gets up to here, which is 1 litre, and then that will give you the time it takes.
The test proved that the connectors work as intended and were welcomed by the nursing staff, who also gave amazing feedback on the performance. Or ended up being more of a side project due to the decision to base it on locally available off-the-shelf components. The choice was to base this system on a 12-volt car battery as the main power source, as car batteries are commonly used in Sierra Leone for powering household appliances as well, as most of the country has no access to power. The final concept for system power is a portable power pack with locally sourced components and a 12-volt deep cycle car battery as a power source, which would be able to power the suction pump for 2 hours during a power cut. By placing the components in a battery box, the system would be protected from environmental impact and would allow for the system to be transported anywhere around the hospital. With regard to the challenges of lack of consumables and frequent power cuts, the use of Masanga surgical suction pump can be improved with local on-the-ground FDM 3D printing of medical tubing connectors to connect mismatching consumables and installing a portable backup power pack built with locally sourced 12-volt car battery plus locally sourced gadgets. The staff of Masanga was thrilled for this possibility to improve the use of the surgical suction pump. The practice of 3D printing tubing connectors could lead Masanga towards the possibility of locally producing various other medical consumables that they're in need of and that are fit for improvement to local 3D printing. This practice would, however, require the engagement of a designer or a biomedical technician to aid them in discovering the possibilities for improving the use of other medical devices as well. If this practice is proven to be successful, the staff of Masanga has the intention of expanding their production and turning towards a decentralized local manufacturing approach. This means that in the future, the team of Masanga could be able to produce consumables for other regional hospitals as well, who have similar problems with lack of consumables. As for system power, if the solution is proven to be successful, the same principle of powering could be applied to other surgical devices as well. A possibility to look into making a single system that will be able to power multiple devices could also be an interesting opportunity. Together with the client, we have decided to continue this project after the graduation, as soon as the COVID crisis settles down. The goal is to continue the project on the ground with a few-month-long field trip, a period during which the manufacturing of the connectors would be tested and the performance of the connectors could be brought to a TRL level 7. Which means that the system prototype would be tested in the operational environment. During this field trip, the goal is to also train the local staff on how to independently manufacture the connectors without the need of an expert. This field trip would also make it possible to locally source the components and build the system power together with the locals and map out how and where components can be fixed or replaced in case of a failure. Thank you very much for your attention. I will see you soon after the commercials.